Hello everyone, welcome to the Verification Features Conference Austin 2023. Here we have a session for UVM for AMS verification. Here we have experts Peter Grew and Stephen Holloway. Speaking about Peter Grew, he is from Renesas. He is a distinguished member of technical staff. He has 20 plus years of experience in mixed signal design and as well as EDA tool and methodology development. Peter has led many high-value production devices. In the part, Peter is the chair of SV-AMS and a key contributor to UVM-AMS and 1800 adapter discussion. Peter has presented at many conferences and is recognized for his skill in mixed signal verification. And speaking about Stephen Holloway, he has 20 plus years of experience in digital verification, including ERM, OEM, UVM, and formal property checking. He has led the verification of large-scale consumer SoC projects. He joined Dialog Semiconductors in 2011 and previously worked for Dolos, NXP, and Trident Microsystems. He joined the technical ladder in 2015. Steve has presented at multiple external conferences, including a panel session at DVCon US. He participates in industry standards bodies and has contributed to Accelera UVM-AMS working group. From here on, Peter and Steven will take over the session. Over to you, Peter. Thank you.
Thanks very much for that introduction. So we're going to go over what Stephen and I did probably about a year and a half ago to form the basis of the UVM mixed signal standard. There has been contributions by other members. Some might be there today. One of the key EDA companies that we've worked with has been Cadence, so I need to mention them. And we work closely in a small group to try and get the fine details sorted so we can get a standard out. The goal of the standard was to try and reuse everything that we'd got available and not have to make any changes, and to make it easy to adopt. So we're going to go through the slides. It'll switch between Stephen and myself just due to the different skill sets. Anyone who says they're UVM and mixed signal expert, I don't believe, because you can't absorb all the information to know how an analog simulator works and also be someone who knows the in-depths of UVM. So with Stephen's knowledge of UVM, my knowledge of mixed signal, we work together, and I can just about understand some of the UVM stuff he does, and he can just about understand what I'm doing in AMS. But between us, we managed to solve a lot of the technical details that form the standard. So over to you, Stephen.
Thanks, Peter. So this part is really to discuss why develop a standard for UVM-AMS. Well, really, it's because we want to try to extend UVM into the mixed signal domain, which is the industry standard methodology for developing reusable metric-driven verification components. And UVM mixed signal is basically like an appendix to the UVM standard, which allows UVM to be more mixed signal aware, so that we can improve the verification of those analog and mixed signal designs to apply the same degree of thoroughness that we get with constrained random metric-driven verification. So it was originally called UVM-AMS, but the focus is really to support all mixed signal systems such as DMS, discrete mixed signal, real number modeling, SPICE, or a mixture. So therefore, a more appropriate title is really UVM-AMS. So if we look at the, where we want to use this sort of metric-driven verification within the mixed signal space, well, the sort of targets would be analog performance verification under a large set of digital configuration settings, control system transitions interacting with analog functionality, dynamic control between analog and digital circuits under a wide range of conditions, the sort of things that you might find in a power conversion, charging circuits, things like this. And then finding problems with the interface between the A and D to be able to find the unexpected corner cases that we get when we use UVM. So the randomization is something that gets quite often brought up as being a sticking point with the guys that are doing mixed signal or AMS verification. It's not mandatory, and we get benefits even when if we use UVM-AMS in a very directed way, because we're still using a standard methodology and we've got the ability to plug and play existing UVCs. And we've also got things like the rich debugging that you get with UVM and the messaging scheme that you get integrated with the simulators. Next, Peter. So what are the requirements to get, for really the requirements for the UVM-AMS working group to develop something? Well, as I said before in the previous slide, applying UVM methods and techniques to AMS circuits and systems. So allowing, real number modeling and DMS to allow a single environment to work, whether it's the target DUT is DMS, real number model, or AMS, simply by changing the abstraction of the DUT. To be able to extend existing UVCs into the physical layer, so enabling AMS verification, and then allow predictable coordination of stimulating, measuring a signal, be that in DMS, AMS, whatever, to preserve this sequence item abstraction mechanism that's used in UVM, to keep that independent of the AMS signals, electrical real number model, UDT, whatever you're using to model that sort of thing, and to eliminate the need to rely on conversion elements to change the abstraction level of the DUT signals. And to try and, well, obviously to use existing language standards, because changes can take years to get agreement, and you just simply can't move forward with something like that. So we've got to operate with what we have already available. Thanks, Peter. So the next section is to talk about the what we need to do in order to make all these languages work together nicely. Is we basically talk about the architecture of how we make UVM work connect to a mixed signal. Sorry, I think we don't, Peter, because I think we talk Peter's section.
Yeah, sorry.
About the simulated behavior.
So one of the key things when running even just Verilog AMS is understanding how the simulators start up, how the analog solver gets a DC operating point, how the variables are initialized, because it's quite easy to write code that you run and you think's working, you make a change and somehow it's not working, and it's because of some of the assumptions you might have made. So these are some slides I've put together and have been quite useful for many teams over the years. So the classic is, variable assignments, initial blocks, all execute at the same time, but the order in which they execute is indeterministic. So you can get race conditions. You might make a change to a file and move an initial block above another one, and sometimes you go, oh, how come that one's initializing before another? So it's trying to make sure that what we write is guaranteed to work. And the correct value between the digital and analog engines is obtained, that you don't unexpectedly get a result that causes a checker to fail, and it's because you've not aware of how the synchronization works. And knowing the effects on the DC operating point of the analog solver, when certain at the startup, such as like transition, AMS delta, above, Laplace, etc. Knowing how they work when a DC operating point is done. Now, each analog solver has many methods of doing DC operating point. So once you've gone past the sort of standard one everyone uses, and the simulators try and converge, you're sort of on your own. So you do need to really understand DC operating point and make sure the circuit converges very easily. A classic one I see people do is go, well, I can't get the DC operating point, I'll just tell it to skip the DC operating point and just wing it. Yep, that winging it will probably cause you other problems later on, because transition filters and everything will not give the output that it should have done at DC. And the other thing we wanted to be able to do was enable the UVM environment to actually reconfigure the whole analog test bench prior to DC operating point. So rather than having to, the classical AMS setup was, if you didn't want the cap there, you'd have to netlist it without that cap instantiated, where actually if you take a step back and used AMS and use the way the DC operating points and the simulator started up, you can actually reconfigure the cap before it's done the DC operating point. So it means you could end up with a single test bench that each test case could reconfigure for different things. And that has been very powerful. And other things that we found while at Renesas developing some of this is, adding debug stuff in when DC operating points fail. The classic is you fail to get a DC operating point. The simulators give you a bit of a hint, but not much. So we've done things like add an initial step and a strobe statement that sort of dumps out information that allows us to debug it. The other thing to take away is #0 I've seen it in common practice to solve digital sequencing errors, and really that just shows poor coding and a lack of understanding of how the simulator scheduler works. And when you're dealing with mixed signal, #0 has other effects, so it might solve your problem in the digital world but introduce another one in the analog, so you need to be really careful on that. And one key thing that caught both Stephen and I out is you must raise a UVM objection before the DC operating starts, otherwise you actually have the simulation finish. So a lot of this has been put into some of the template code. So a bit more detail as to how the simulators actually start up. So the first thing it does is all variables are given their initial value. So if you declare a real with an initial value of 1.2, it'll get it. If you don't declare a real with a value, it'll take what is written in the LRM, which is 0. Ints will take 0, etc. If you've got a class defined and it's calling the new construct, it will go and construct it there and then. If you don't call the new constructor, it's just a null, a class with a null value. After that, the analog initial blocks are then executed. Now, analog statements aren't allowed to use out of module references. So actually the order in which the analog initial blocks are executed doesn't really matter. So in the analog initial block, you could initialize some analog variables if you haven't done it a variable declaration. You can call some other functions like $analog node alias, port alias, which are sort of ways of doing out of module referencing. Once the analog initial blocks have done, which tend to be very small and quick, it passes control back to the digital simulator. The digital simulator now will start executing all the initial blocks and any process until they start to consume time. The order in which all these initial blocks and processes, like an always at block is a process, are initialized is indeterministic. It might work in one scenario and then you find it fails in another, and that's because you've relied on a sequence of initialization. So it's always best to assume that all processes at time 0 come up in a random order and make sure it's robust. So as soon as the digital goes, I'm going to start consuming time. It stops there. It hands back control to the analog solver. The analog solver will go, I've now got my initial set of digital outputs. It's taken a guess of what the digital inputs are. I'm now going to try and get a operating point for the analog circuit, which might iterate through the RTL code a few times to actually get a solved operating point. So the best way to make sure you get an operating point quick is you make all the supplies and current 0. All your digital outputs then are 0 as well. So it's an easy one for it to solve. And I've got very big circuits where operating points take, 30 seconds. We're talking 500,000 plus transistors. So once the simulator gets started, we have to progress each of the simulators in turn, and unfortunately, although the digital guys would like to think they're in control of this situation, it's actually the analog simulator is in control. The reason being is it's got techniques that allow it to roll back in time if something isn't right, where digital is an event driven. Once all those events have been consumed, it can't roll back those events easily. So what happens here is the analog solver will jump ahead to a new time point, and that time point could be due to an analog statement like cross, above, or timer that have told it you must stop at this point, or it could just be that's the internal time step it's chosen to use based on the derivatives of variables and electrical nodes in the circuit. So at this stage, it hasn't committed that to the database. It's just got that in memory. It then goes back to the digital. The digital now advances. It creates some digital to analog event. So the analog goes, thanks, mate. I've just spent 5 minutes getting the solution, and you've now created a digital to analog event. So I've got to scrap all the work I've done and restart it and create it at this time point. So after that, the two engines are in sync. The analog advances again to the new time point, and then the digital does. So the digital always leads. Any digital to analog events cause the analog solution that it did have to be scrapped, and it backtrack and create a new one. And any digital variable that's used within an analog block is treated as a D to A event. So be careful with that. So what can we do with variables? Because we obviously are going to have to communicate between the two engines. So the analog solver has access to, or you can use real and integer and string variables, and it can read, the analog engine can read and write to them. I would just avoid string data types. The support's not great, and the LRM is also not great in that respect. But also the digital engine can read the variables, reals and integers from the analog engine using event-based statements. Similarly, the digital's got reals, integers, strings, logics. It can read and write to them, and the analog solver can read those as well. So out of module references, I've just said, are not allowed as they're not part of the matrix. So what we're now going to cover is the mixed signal bridge to the analog resource. So this is really the main component, the physical component that gets UVM to be able to speak to the actual DUT. So we start by the mixed signal bridge, which is a system Verilog wrapper. That then instantiates what we call the analog resource, and that analog resource could be DMS, AMS, real number model. It's basically, you use the language that matches the abstraction of the pins that this analog resource is driving. Not to try and put connect modules in or any other adapters. So if you're running a pure digital sim, this analog resource would be system Verilog, and it would drive out whether a real UDN or whatever you've decided to model as. The other two components are a proxy. Now the proxy can't contain wires needed for logic strength, but what we did put in the proxy is methods that allow us to take data from a UVM class-based world and push that into the analog resource to go and do something. Now that might be quite good, that you get a request, go and generate a sine wave. So the proxy will go to the analog resource and go, just generate this sine wave. It could be that you actually want the proxy not only to push a request into the analog resource, but actually push it and block the return until that operation has happened. In addition, the proxy is used to get results out of here. So it could be that you want to get the voltage of the plus pin. So the proxy would query, call a function in the analog resource to go and get it from that pin. And because it's a function call, it now means that works whether it's AMS or DMS. And then we've got this other one called monitored, which would take a signal in here and constantly feed it back up to the proxy. The system Verilog interface is optional. They're really there for digital wires. So if you had something that like an I2C to start off with, that then needed to do other things, you could keep your interface for the I2C and add the proxy in to allow far more finesse in the analog resource to control the I2C pin. So the extra pins on here, like ref VDD, ref VSS, they're there in case any connect modules need to be inserted. The plus and minus here were just an example of what you might want to drive out. Now at this level here, we declare all these pins as interconnect. Now that's a system Verilog keyword and says it's a typeless net. It's generic. The advantage of doing that is it stops people accidentally writing code here that would try and connect to it, like an assign statement and things like that. The reason we use out of module references between all of this is not because it looks fancy or anything like that. Verilog AMS has a restricted set of IOs that you can use, and it doesn't understand the difference between packed and unpacked. So the way to get around all of this is use out of module references and call functions, and that simplifies it. It also means that you haven't got a massive amount of IOs on here. So as an example, what does the analog resource look like? Well, we've got the bridge here. It could have some parameters. We declare the ports as interconnect. We import the UVM package. We've now got this new mixed signal package. There's not that much in it. It's just got some boilerplate code in it that's needed. We've got the standard macros, and now we're including these UVM macros. And then what we've got for an AMS version for the analog resource, we've got the plus and minus pins, the parameters, and a get function here. And then similarly for the DMS one. Now, so that these out of module references work, we have to make sure any function calls between the AMS version of the analog resource and the DMS version are the same. Unfortunately, functions within AMS are very old school. Their definition is basically back to the Verilog 2001 standard, and that means that the function in the system Verilog version must match it, and functions in AMS must have an input even if it's not used. So that's why we've got the dummy here. These includes here are to enable messaging, which Stephen will talk about in a bit. So the analog resource for logic signals, the analog resource must be there to convert the logic to the abstraction. So it could be that your DUT is just actually a real number, it could be a UDN, or it could be electrical. And the idea is that you write the conversion in the analog resource, you use the proxy to control that conversion so you can change ramp rates when the X is detected, etc. If, say, your DUT pin was just pure logic, you could just do a short from input to output. Classically, real number modeling, you would drive, if you were to generate a sine wave, you would generate the sine wave in the UVC sequencer and drive out each sample one at a time into the analog domain. So you'd get some sort of effect like that. And while that works for DMS and real number modeling, that won't work when you come to run it in AMS. Each one of those steps there will create a digital to analog event, which A, will slow down your simulator, but B, you will not be able to get enough finesse on the signal to get a quality, to be able to take parametric simulation results. So really the biggest change that is coming is work from classical UVM to running classic UVM mixed signal. Is the signal generator now has to move to the domain that it makes most sense. So it ends up having to be in the analog resource. So a generator could be made up of numerous things. I've done a sine wave here, but it could be made up of a RAM and all the rest. So what you would do in your UVC is where you would have done in the past, generated a discrete sine wave like this. Now what you do is you pass 4 properties over for the sine wave. You send the frequency, phase, amplitude, bias. The analog resource then generates the sine wave. In AMS terms, that's a couple of lines of code. In DMS, you're then going to have to regenerate this square wave there. But what it means is the interface from your UVC to the analog resource is the same. So this is where I see the biggest challenge for adopters of this, and probably the biggest challenge for vendors, because I can see the classic UVM verification engineer trying to send in the step waves, and he'll get some sort of results, but later on the analog engineer is going, but that waveform doesn't match what I see at block level in pure spectre. What's wrong? And trying to track something like this down is quite tricky. Over to you, Stephen.
Thanks, Peter. So let's take a step or two back into looking at what the proxy class is from a sort of UVM perspective. So this class is basically just designed to hook your UVM agent, driver, monitor, whatever, in to be able to communicate with the analog resource. So it's, as the name suggests, it's a thin layer between UVM and then the implementation of the analog resource. It's kind of an alternative style of connection between the UVM class, class-based world and the system Verilog static hierarchy. So it's kind of like an alternative way that we hook things up to perhaps like a virtual interface, traditional virtual interface hookup. So we have a proxy class that's derived from a class we've created called UVM-AMS proxy, which is in turn derived from UVM report object. The reason we do that is that then we can issue messages under that report object context, which can make sense potentially inside the UVM reporting hierarchy, and we can turn verbosities up and down according to different layers that we have in our reporting hierarchy. So that's why we do that. It's not mandatory, but it helps the messaging. The actual class definition or implementation is placed inside the SV bridge module. It's called MS proxy. This is a sort of pattern name, and that's the actual so-called concrete class implementation. The instance name has to be UVM__UVM-MS proxy because we use that hook for our messaging to work. So a handle to the proxy class is then in your sort of module-based hierarchy, you'd obtain the handle to the out of module reference or hierarchical reference, and you would then place that handle in the UVM config DB such that the UVM components then can do the hookup based upon that that handle. So it's really the same way that we wire up system Verilog virtual interfaces using the config DB. So as I said, I think at the start, the implementation of the proxy API methods. So the proxy class itself, which you would extend in the bridge module and make an implementation in itself, we can consider it to be, some definition of some API methods that we want to actually implement, and then in turn we execute those in the actual analog resource. So that's why we called it a proxy pattern, because it's not really doing any work, it's just passing the work to be done in the analog resource. Thanks, Peter. So if we look at the actual picture of how this stuff sits within the sort of traditional picture of a UVM agent, if we have a UVM-AMS agent, we can see that we have the sequence of driver, monitor, configuration class, virtual interface, and then we've just added in the animation, we've just added the proxy class. So that's a handle to the actual concrete class that we see inside the MS bridge. That's passed into the agent via the config DB. And that then will allow us to communicate to whatever methods we have in the analog resource. So it could be, as Peter mentioned earlier, it could be things like setting up a sine wave, setting up a ramp, monitoring a signal, passing information backwards or forwards into the analog domain. So we had a couple of rules to make this all work nicely. So we have a proxy which is always present inside the bridge with a certain instance name. The system analog interface is optional, but it must be inside the bridge. So we could use that for sort of traditional sort of logic drive if you wanted to keep that in your mixed signal resource. And the agent then could, if we're moving from a traditional UVM agent to a mixed signal agent, we could use the factory overrides to extend the pure digital solution and put in the proxy and modify the driver and monitor and whatever we need to do to make it work. So this will all work with the UVM way of working, where we extend things and we use factory overrides. So here's just some snippets of code to show us, just to go over the hookup and how we define the proxy. So on the top left, you can see there we've got this idea about a proxy template. So this is actually for a cap analog resource for some kind of capacitor sort of functionality. So we extend that from UVM-AMS proxy, and we define some virtual functions for setting and getting the capacitance. So these are not actually implemented in the template. This is just defining the API. When we move over to inside the bridge, we then actually define the MS proxy class, which extends from this API. So it must implement those virtual methods that we have in the API. So then we fill out what they actually do. They don't do much. They basically go in and call the corresponding functionality, which is defined in the analog resource in this case. So we can see that we have a set handle and a set name in the constructor further down inside the bridge module. Then if we look at the bottom, that just shows you how we could set up the connection into the UVM config DB within inside an initial statement there. We've basically setting something inside our UVM test top, inside our env. So we'll have something called C proxy inside the env, which is set to the proxy instance under icapbridge.uvm-ms proxy. So that's a way we can communicate and broadcast the position of that proxy handle into our UVM environment, just like we can with a virtual interface.
Thanks, Stephen. So when it comes to AMS, we need to think about how these proxy functions will work. So we discussed that there's about 4 methods. So I'm going to go through them. The first few are fairly trivial. The next slide is you need to pay attention, otherwise you can lose the plot. So when you call set ramp here, it passes in a value and a transition time. It calls void. I call set ramp here. The reason it's void is because Verilog AMS, all functions have to return something. Should have mentioned that earlier, apologies. So this would push it into here. Those would update some local variables here, and then the target value and the rise and fall would get pushed into the analog to the transition statement there, and then that would cause a D2A event, and then the analog would get the updated values and carry on. The set ramp is, as I said, just a return value, but we have to do it. Then the other one is maybe you just want to query what's the voltage via the UVC. So you could call get voltage. It would have to call the iCall get voltage with the dummy input that you don't use. That would then just use the AMS construct to get the voltage between the plus and minus pins and return it as get voltage. Now, if this was a DMS model of the analog resource, it's a lot easier to code some of this up. You don't have some of these restrictions. Now, when you do call get voltage, the key thing to remember, it's an interpolated value. It doesn't go and create an analog solution at that point. The idea being that the the interpolated value should be so close to the real one that it shouldn't affect your results. and then that would return it back up here, and then that would return it back up into the UVC. And the other way is monitored. Now, in a monitored one, we basically have to monitor the analog value. This is just using an AMS delta function that will generate a digital event to update a digital variable from an analog one. So every time that changed, it would be monitored by this assignment statement here. This assignment statement here would update the value in the proxy, and so you would, in effect, within the UVC, appear to see a continuous signal from the analog resource. This, in AMS terms, is very costly, so you really wouldn't do that unless you had to. What you could do is put some sort of monitor in here and just return the results of the monitor back up, which would be far more efficient. The push sync is quite involved. So, when you say change a value like the set ramp, you pass in a value like that, it's translated in the analog terms to like that. And it might be that you want to set the ramp to go up to a voltage here of 5 volts, and you want the UVC or the sequence to be blocked until that happens. So somehow we've got to get feedback from the analog back into the digital. And remember, there are two simulator engines running here. So making sure that they're synchronized and they're speaking to, and one blocks the other, is key for this to work. So what we came up with was this idea that you've got your new voltage that you're wanting to go to, you've got the output of the transition which is now being applied. I'll take the difference between them. As long as it's less than a tolerance, then it assigns it a 1 or a 0, and that for me is end of transition on this VDC. You have to have tolerance because, you know, analog solvers have tolerances on numbers, you know, so there will be a subtle difference. Yeah, so the idea is what we want is the function call from the UVC stack all the way down to the analog, the proxy into the analog resource to be blocking until this event has finished. And so you can then use at end of transition VDC to block how it carries on. People go, well, I'll just use a hash delay. I've asked it to ramp the voltage up in 5 microseconds, so I'll just do a delay of 5 microseconds. Analog solvers have tolerances, so it might not be 5 microseconds. It might be 5 microseconds plus 1 nanosecond. So you can't always rely on the hash delay giving you exactly what you want, and depending on what you measure, you could get the wrong result. So we might also want, you know, the UVM agents to be reactive to conditions in AMS. So this is another way that we can do that. So this is an odd example. We've chosen set capacitance. You normally wouldn't change the capacitance during a simulation, but this was just to demonstrate it. So we've called the proxy set capacitance. We've given it a new set of values, and then we've called wait cap end of transition. So the first thing that happens is it goes into the function within the proxy to call set capacitance. Set capacitance then calls the I core, which is the analog resource, and passes the values into there. The first line here updates the local variables for the capacitor. I then update the local value of the cap end of transition by looking at the cap out and the current value and giving it a tolerance. That's so I update it at this point here to make sure that I am using the result of this current time of the last time step and the new digital value. That updates that value there. That will update that value there, which will then go to this reg here, which will then go to that value there, and everything is then synchronized, so we now know that this will block it. At the next analog time step, this AMS delta will toggle, cap EOT will toggle up here, and then that assignment statement will update that one there, and then that will update the wait statement there. So we've now got guaranteed synchronization. It is quite involved, you know, but we've tried to make the example as simple as possible. So for a logic signal, there's various ways in which you could code up the analog resource. So what I've sort of said here is I've got a DUT pin with various abstractions, and I've got some sort of logic signal coming in. Let's call it I2C. So the implementation of that, of the analog resource I would use if it was logic, is I would just do an alias D in to D out. I would have template functions for all the functions the proxy might call in here. If it was a DMS or real number model, the D in would be assigned from an out of module reference here, and then from that you could decide every time D in changes, go and ramp D out over a set period of time. Again, you've got to have the functions here to match it. And the same thing can be done in AMS. So, you know, chances are you're going to have, if you've got a DUT pin that can have 2 abstractions, then you're going to have 2 implementations of the analog resource. If you've got 3, you're going to have 3. And then you've got to make sure all the functions and the boilerplate code is common between them. And the idea as part of the committee was to try and provide some sort of examples using, you know, passive elements. So what I'm going to do now is pass over to Stephen on the phasing requirements for UVM mixed signal, and he'll discuss that.
Thank you, Peter. So there are extra phasing requirements we need to think about when we're simulating with mixed signal DUT. So our mixed signal bridges will have parameters. Typically, these will equate to sort of component parameters in the mixed signal domain. So UVM needs to have a means, or UVM mixed signal needs to have a means to read, modify, and write those parameters before the simulation starts churning away. So the proposal is that we have methods to get and set the parameters in proxy, and then we call those in the right place in existing UVM phases to guarantee a read, modify, write order. We could have added extra phases. It's perfectly possible to add phases to the UVM phasing mechanism, but in order to keep this simple, we keep it in existing phases. So the connect phase is a suggestion where we would actually read the parameters from our bridge module into the agent configuration. Then at the end of elaboration phase, that's the point where we would decide, based upon test requirements, to potentially modify those parameters inside the agents. And then at the start of simulation, then we will call the modification to write back any changes that have been made to those parameters into the bridge. The other thing to point out here in this slide is that in the run phase, we have to consume some time to allow the DC operating point to happen before we actually drive any sequences, drive any tests, so that the synchronization system works. So we also recommend to have in your base test basically a 1-step delay in order to cause this DC operating point to happen in all your tests that you derive from that. Thanks, Peter. So here's a slide which shows you a little bit bit more detail about the parameters that you might be reading, modifying, and writing. So, for example, we've got an AMS bridge with a parameter on it called resval. In order for us to then modify that, we'd have this get parameters method we can see in the proxy there. So we would read that iCore R series val, which is set up by this R series val assignment inside the analog resource there. So during the read phase, we'd read that back. We call that read in our agent, copy it into the configuration class, which we're returning from this function call, and then modify it during the modification phase perhaps inside our UVM test, derived test, that we'd have some modifications on some of those parameters. And then before we actually start to consume time, we'd then call the set parameters to then essentially copy back those configuration class modifications back down into this iCore R series. So that's basically showing you how the code works for the read, modify, write. And this slide just shows you a bit more detail about where the code snippets in terms of the UVM, where you do that read, modify, write. So during the connect phase, we pick up inside the driver connect phase. You can see on the left-hand side code snippet, we would call get parameters inside the proxy handle and copy that into our configuration class. Then at the end of the elaboration phase, here I'm basically seeing end of elaboration phase hook inside the test level. So at that point, we might set up a configuration setting, so this inside an agent, and the configuration class here, CFG, the R series we set up to be 10K. And then as we move on to start a simulation phase, we're actually then calling set parameters and passing in the configuration class that we've actually modified. So this would all sit inside the MS agent, and the user would only really need to call the modification at the test level to change any parameters that they need to do. Thanks, Peter. And then the point here of this slide really is to say that inside our run phase, we need to first of all raise objection, because as soon as we start consuming time without any objections raised, then UVM will actually terminate. So first of all, we'd have to raise an objection to the test termination, then consume hash one step of time, and then we can go off and start our sequences after the DC operating point is finished. So now we're moving on to the UVM messaging requirements. Just as in this traditional UVM, we need to be able to filter and control generation of messages from the analog resource. So UVM's got control in the component hierarchy, but the analog resource isn't part of that component hierarchy. It's actually inside the module hierarchy. But if we extend, as we've said before, the MS proxy from a UVM report object, that actually gives you reporting context that you can control. So a set report handler can then redirect the handling of that report object somewhere into our UVM hierarchy. Typically, that would be the enclosing UVM monitor or agent. So then messages from the bridge level and below can use that proxy context to send them up to wherever we want inside the UVM hierarchy. And then we can control the verbosity of that part of the hierarchy using the powerful reporting control messages that we have, control API that we have. So the actual macro that we use is the UVO info context, which isn't probably not a particularly commonly used reporting macro, but basically it takes the final argument, which is a reporting object, to provide the context, and that basically then sends your UVM messages into that report object context. The messaging macros call from the analog resources use upscoping, as Peter will describe later on. It's also recommended for the users to include the %m in the UVM message body to actually get the physical path of where the message is coming from. So here's the sort of overview of how it all works. If we look inside, dive inside the MS bridge level, we can see there's a code snippet there where we're using the UVO info context, and we're providing the final argument is our proxy. So that's the class that is derived from a UVM report object. The hookup at the connect phase inside the top bit of code there, we can see that's the actual monitor inside our agent. And what we're doing is we're in the connect phase, we're actually setting the report handler of the proxy to be the report handler that is the one used by the UVM-AMS monitor. So that means that all the messages that come from the proxy look like they're coming out of the monitor inside the agent. So that means we can control the verbosity in that particular part of our UVM hierarchy. And you can see on the bottom, they will look like it's coming out of the monitor inside the agent. Next, Peter. Thank you.
Yep, so I'll just go over how you can do messaging from the UVM layer. So the reporting system that UVM provides is really structured around the UVM reporting object, and it's all class-based. UVM reporting macros are not supported in Verilog AMS because you can't import anything. It's based on the Verilog language of about 2004. But within the LRM section 6.8, upscoping can be used. So what we were able to do was basically define, call some functions within the Verilog AMS layer that don't exist, and then it would automatically look at the next level above to see if those existed. So it allowed us to create a set of reporting functions that could be called from a Verilog AMS file that would actually hook into the UVM messaging system. So we provide a couple of files, UVM mixed signal VAMS H. This has to have local parameters for the UVM verbosity to match the enums, because enums are not supported. So it literally is a complete copy of the enums, just with the word local parameter instead. We provide a set of macros, so they're exactly the same format and sort of syntax as the classical UVM ones, except we put _MS_ in between. We provide a similar one for system Verilog files for DMS, but basically we don't need to include the local params because you've got access to the enums. Then in the bridge, we include another file that wraps up the tick UVM macros to the same name so that you can use, but also it provides the functions that these will then call. So that works fine because you can call these reporting functions from a digital portion of a Verilog AMS file. But how could I use the messaging system to get a message from something in the analog domain? Well, it is possible. This is a very crude example here. I've basically gone, if the current or this variable is greater than 1 and this variable hasn't triggered, set it to 1, else it's set, if it goes below this, it's set to 0. So there's a bit of hysteresis in there. Then I've used the AMS delta on that variable, and these settings say when it toggles by 1, then I can format a message, because Verilog AMS does not support the $S format F or $S format S syntax. You have to cast it to a string first. Then if it's gone above 1, we can call the macro here, and then that would go and write out the information. Key thing here is most of the UVM messages will not be triggered if there's a convergence failure, which goes back to one of the first few slides, was in your Verilog AMS file, always put an at initial step to report all the findings. Over to you, Stephen.
Okay, so this is just more detail again on the messaging and how the flow works from calling a message and to actually arriving at the report object. So from the analog resource, we call the UVM-AMS info macro. That in turn, as Peter said, via the upscoping, it calls basically a function that's declared inside that in the macro where we're calling UVM-AMS info, and that in turn calls UVM info context on and provides a fixed name for the reporting object, which is the __ UVM-AMS proxy, which is why we mentioned that right at the start of the presentation, that we had to have a fixed name so that this macro will work each time. So then when we use that proxy context, we can see that we have, and the message down below, we've got the wherever the context we've pointed to, which in this case is the V agent inside our top environment. A couple of things that we found out when we were messing about with looking at messaging and reporting is that there are a couple of issues with the existing UVM reporting which don't work very well with mixed signal. First of all, the UVM printer methods print real, It uses %F formatting, which doesn't really work very well for small values. So we recommend a change to %E such that it scales nicely when you have very small values. Otherwise, it would just basically, round down to 0, as you can see in the example below. The farads and Henrys are both 0 there, but the farads are 0, but in reality they were 1e to the -9. There's another issue that the timestamps were using time rather than $real time in UVM 1.2 onwards in the composed report message. So therefore you could get very small time values essentially truncated to 0. So there is an issue in the Mantis there, but we've basically worked around both of those issues by overriding the report server to implement that, change the functionality on these things, the print real and also the report compose report message. And these are provided in the example code.
So one of the things we have suggested is when you're using UVM mixed signal is go for the dual top approach. So splitting your class-based world into, we've called test case, and your physical world into the test env. The advantage of doing that, one is a lot of hardware accelerators can then take this and apply it straight away and keep the software outside of the hardware accelerator. Secondly, it means you could have a completely different test case setup for a test env that is using DMS instead of AMS, yet the whole test env hierarchy can stay the same. So it's not new to UVM because it's just known as the dual top, but it is one that we're sort of actively saying is the best way forward. So just to summarize, just a few files that we are going to have to provide. We did try and keep them to a minimum, but as I said, there's going to be a package. There'll be a mixed signal file for the resource, a DMS one and an AMS one, and then a mixed signal file for the actual bridge itself. So the work is still ongoing. There's still some discussions currently happening about the messaging to fine-tune it, mainly because we realized there was a hole in the messaging system that we focused a lot on how messages are done from the analog resource up into the bridge, into the UVA, into the agents, but actually you might need to report a message from a model somewhere down in the DUT. And so we want some method of using the same UVM reporting that works in that area. So this is subject to change. So we've just about out of time, so I'll stop at that and hand over to the chair for any questions.
Yeah,
The organizer, you
for question and answers. If anyone having any questions, I can.
Okay, that's one question. I'm still trying to understand. The main question is, so you have the proxy and the system verilog interface. You have those two different ways of doing things. It seemed like you had both there in one time. Is there a use case for that, or is that just something?
Yeah, so what you're referring to, the audio is not amazing, but I think I got the idea. There we are. Oops. Oh, hold on. Where's the next slide? I'll find it. The question is why have we got the proxy in the system Verilog interface, and when would you have a scenario that you would have both?
Right.
So if the DUT pin is meant to model something electrical, some sort of electrical aspect all the time, like a sine wave or, analog test bus, you would never have the system Verilog interface there. If your DUT pin was something like an I2C or a digital pin like an enable, then that might be driven from a UVC via System Verilog interface. And what you would do here is your analog resource would be there to convert from the logic to whatever data type you've got here, and the proxy allows you to fine tune that. Yes, you could put connect modules in. The problem is controlling those connect modules is not easy. And if it's DMS, there might not be any connect modules to convert from logic to a UDN. You'd have to do it yourself. So the idea is that you'd use the proxy to enable you to fine tune that.
Okay. This mixed signal design got digital signal. Right. Digital will just pass code. All right.
The other question is, so you presented this to Accelera, and I mean, have they accepted it, or what's the timeline?
Both Stephen and I have been part of the UVM mixed signal since it started a few years ago, and there's about a core 5 of us that speak every 2 weeks. And as I said, we get lots of emails between us and Cadence, who are helping out quite a bit on this.
The goal is to have it complete, ready for submission by DVCon 2024 March.
Is this available anywhere for anybody to try?
Not at the moment. We created an initial example that has been shared with the EDA vendors.
Okay.
Now the messaging is been updating. We'll need to do that again. And that's basically really just to check that it works in all the tools. But as we've gone through the messaging, we've actually found that we need some very minor changes to the UVM itself and to Verilog AMS. Luckily, as chair of System Verilog AMS, I can get those through. So we should have a new Verilog AMS standard out later this year. And one of the other members of the UVM committee is also chair of one of the members of UVM Mixed Signal is also chair of UVM, so that sort of helps us push things through. We've tried to avoid those changes, but we've got to that stage, so it probably would be next year, beginning of next year, before all the standards are out that mean that this can be used.
Hello,
I'm sorry, I haven't heard any of that. The audio didn't pick any of it up.
So my question is about monitoring. So how you transform mixed signal to transaction?
I think you're going to be next to the microphone. We really can't hear you.
Too close to that. Just talk.
Not quite.
Oh.
You might have to stand near the front and ask the question.
Hello, sorry, Salem, NXP. So I have a
hi there.
question
That's
about.
a lot better.
Okay, it's about UVM monitoring. My question is how you translate the mixed signal to transaction, basically.
Stephen, do you want to answer that?
Yeah, I think, well, okay, so I think you need to identify the area of interest, because when we're talking about transactions in traditional UVM, we're talking typically about things, a sequence of events that happen on a bus or a bunch of signals and that conform into a protocol. Now, it doesn't make sense. Well, it may, I guess in the general, setup, it doesn't make sense to, if as soon as the voltage changes, to create a transaction based on that. I suspect what you would do in your monitor is you'd look for a sequence of interesting events or some exceptional condition where you would then be firing off a transaction that makes sense for you to then do something within your UVM environment. But yeah, it's down to that's all down to the user at the user level, right? We're not saying this standard doesn't sort of define exactly how you you create some kind of scoreboarding mechanism for some mixed signal DUT. It just talks about how you can communicate between the class-based world and the analog resource.
So if you had a DAC that was generating a sine wave and you wanted to check the frequency, the way you would probably do the monitoring is that because sampling it in AMS is not going to give you a good enough quality, you'd probably build the way of detecting the frequency in here and the amplitude, and every so often sending that value up to the proxy that then can be used by the monitor.
Yeah, that's all from the side. Yeah, thank you, Peter and Stephen. Thanks for your time. Thanks everyone, and bye.
Thank you, everyone.
Thank you.